Hello, I'm Andrew Kolbert, President and Chief Technical Officer at Avomeen, and I'm here to talk to you today about food contact compliance, particularly the experimental design for migration studies, which are key to food contact compliance. Food contact compliance is to ensure that there is no transfer of constituents of packaging and other things that contact food, mostly packaging, in quantities that could endanger human health or would bring about an unacceptable change or deterioration in the food itself. Now, there are a lot of things that are prior sanctioned, and food contact compliance is achieved by just doing end-use testing on your end product under 21 CFR 177, various monographs. Mostly these things are just to show that the extractables profile is more or less similar quantitatively to prior existing materials, so that every manufacturer doesn't have to go through an extensive testing regimen in order to get their product approved. Migration studies are reserved for things for which there's no prior sanction, new materials that may contact food. A migration study needs to be done to satisfy the FDA's requirement that sponsors of a food contact notification should provide information sufficient to permit estimation of consumer exposure. The migration data is intended to provide estimates at the highest level of migration to food from the anticipated use of the food contact substance. In case where the use level of food contact substance is low, it may be possible to dispense with migration studies, like an additive that you use at a fraction of a percent. You assume that 100% of it migrates into food, and if it's still safe, then you're good to go. But in a lot of cases, you can't assume that, or the numbers are too much, and you have to go on and do a migration study. Okay, some important levels to note. Half a part per billion in the diet. Now, this is in the actual dietary consumption, and I'll say a few words about how to calculate that, or 1.5 micrograms per day. This is what's known as the threshold of regulation. Below that, there's no problem with bringing a substance into food packaging and its use. It can be a food contact notification would just sail through with no particular toxicology requirements, or you could just apply for an exemption of the threshold of regulation, being below the threshold of regulation. Between half a part per billion in the diet and 50 parts per billion in a diet, you have to do some petri dish toxicology, AIMS and chromosomal aberration testing, just to ensure that there isn't an issue with what is migrating out. However, above 50 parts per billion in the diet, the FDA now considers this a food additive, and now you're in the regime of multi-generational feeding studies of rodents. And in my experience, no one goes there. In my career, I've had one client actually participate in these studies to get their product approved. Normally, one would find a different way of formulating it or a different analyte to achieve the same technical objective, rather than going through these multi-generational feeding studies in rodents. Okay, some math that you may need to be aware of in order to work with migration studies. If M is the migration result in microgram per gram of food for the food simulating solvent, you have a dietary exposure, which is a consumption factor times M. The consumption factor is to account for the fact that all of your food, all your entire diet, is not packaged from that one type of polymer. Now, that consumption factor is usually a small number. It may be 0.05, like in the case of polyethylene, but it may be 1 in certain cases. For example, for materials that are used for infant formula bottles, the FDA will assume the consumption factor is 1 because it is reasonable to assume that an infant gets their entire diet packaged in this type of polymer. And so they don't allow this consumption factor, which is a factor to reduce the migration result into a dietary exposure. They don't allow any reduction. You assume that the entire diet of the infant comes from that package, and that's very realistic for an infant, and that's what's used. But generally, these numbers for adult food are lower than 1. So you have a consumption factor. Now you have an analytical result in micrograms per mil. There's a solvent that you did the extraction in, so many mils per surface area. You assume that a surface area of 1 square inch contacts 10 grams of food, and you have a concentration. So if you have a consumption factor of 0.05 and you use 40 mils in a migration to 4 square inches, and you concentrate, the analytical concentration is 10x, then a dietary exposure of 0.5 parts per billion implies a concentration in the analytical of 100 parts per billion in the method. So these food chemistry calculations are things that the analytical laboratory needs to understand because it drives the sensitivity of the method that they're going to need. If the consumption factor is 1 and you use the same numbers, then all of a sudden you're talking about 5 parts per billion. 5 parts per billion is a heck of an analytical method. That's what drives it. A consumption factor of 1 that drives you to a 5 parts per billion analytical method. And so you need to be aware of these because the lab needs to understand where the LODs need to hit. Food simulating solvents. This is from the CFR. It's also from the Food Contact Notification Chemistry Guidance. But for aqueous and acidic foods, you typically use 10% ethanol. For low and high alcohol foods, 10% or 50% ethanol. And for fatty foods, you can use 95% ethanol in most cases, but there are times that 95% ethanol won't work. And you have to use food oil. An analytical chemist will tell you the last thing he wants to do is analytical chemistry in oil. But sometimes it's unavoidable. And I'll give you an example of the time that it was unavoidable. Time and temperature. The time and temperature should be the most severe that you will ever experience in its typical use. If it is high temperature retort, then you do 250 degrees Fahrenheit or 121 degrees C for 2 hours. That's in an autoclave under pressure, and you can do that with the aqueous food simulants. If it's room temperature, you use 40 degrees C for 10 days, and then you analyze it 2 hours, 1 day, 4 days, and 10 days. And all of these are in the food chemistry guidance that's published. Now, if the only application is a bottle, then just fill the bottle. It's very simple. You just use the bottle, use the jar, you fill it. But in many cases, people say, well, I have a polymer, and it's going to be cast into many different forms. And so I want to be, I don't want to use a particular object. I just want to give you plaques of the plastic, and you can get it approved. And yes, that's possible as well. So for the more general case, you prepare 2 by 1 inch plaques, 40 mils thick, 40 mils so that it is 2-sided migration. So your 2 by 1 inch plaques are actually 4 square inches. With a food contact substance, whatever it is, at the maximum use level. So if you're going to use 1,000 ppm of an additive, then that's the most you're going to use. When you put 1,000 ppm in, even if you might use 500 ppm, because it will be approved at the maximum level that you use in the migration study. So you do the migration study at the maximum level. Migration can be conducted in 4-ounce jars. Some people say, well, I've got a polymer additive, but I'm going to use it for all polymers. It's a slip agent, it's an antioxidant. I want to use it for all polymers, so I don't want to do this 10 times in different polymers. Well, for all polymers, for a polymer additive, you use low-density polyethylene. Low-density polyethylene is a sponge. Everything migrates out of low-density polyethylene. It is a worst-case porous polymer, and nothing will migrate worse out of any other polymer than polyethylene. So you use low-density polyethylene as a proxy for all polymers, and you do your migration study in that. Okay, migrations are performed in triplicate for each condition. Their total non-volatile extractives must be quantitated gravimetrically and characterized. The FDA considers everything below 1,000 molecular weight to be a chemical, so the non-volatile extractives, you need to characterize them so you can understand how much of the monomers are coming out, and are they reacting with anything, and are they creating any sort of anything that could be potentially toxic or carcinogenic. Analytical methods should be as simple as possible, but no simpler. I had someone come to me with a colorant that they want to get approved, and they say, well, can you just do it by UV vis? I mean, it's blue. mean, you can see it. It's blue, right? Just to measure the blue. Well, yeah, I can measure the blue. I can see the blue stuff. But what else is coming out of there that you're not seeing? So, no, you can't do it with UV-Vis. Usually it ends up being LC-MS. So go as simple as possible, but not to the extreme where you're not seeing stuff coming out. All analytical methods are validated. Now, the people that work in the pharma space, validation means a completely different thing than people that work in the food contact space. In this space, validation means triplicate analysis of the actual migration solution spiked with 1/2, 1, and 2x the levels found, with recoveries in the range of 80 to 110%. RSDs are less than 10%. You can also use an orthogonal method of quantitation. Two methods of quantitation will be considered a validation. In practice, nobody does that, because in practice, it's hard enough to come up with one method. You're never going to come up with two methods. So that's almost never done. Third method, which is commonly used actually, is a method of standard additions. And if you show linearity with a method of standard additions, then your method is valid. Okay, let's talk about some case studies. First case study is baking trays. A company was developing a new polymer for baking trays based on 4 monomers. So the baking tray required temperatures as high as 500 degrees Fahrenheit for 3 hours, baking muffins for 2 hours probably, but 500 degrees C, it's an extreme of conditions, but this is what they require. So there's no possibility of doing 95% ethanol. There's no way 95% ethanol is surviving at 500 degrees Fahrenheit. So you really have to do the migration study in oil. So we used Migliol 812, which is this commercial oil, more chemically simple than corn oil, for example, and an acceptable oil at 500 degrees Fahrenheit for 3 hours and 70 degrees for 237 hours. So the balance of the 10 days, it was just kept warm. So you make muffins in a baking. You bake muffins at 500 degrees Fahrenheit for 3 hours, and it sits in the muffin tray. So your baking tray for 10 days. And here's your sampling at 1 day, 4 days afterwards, 3 days afterwards, and 10 days. Now, for the experimental design, we took sheets of this and cut it into 2 by 1 inch plaques, 0.1 inches thick, which is more than thick enough to have two-sided migration, and did the 4-ounce jars. Now we ran control samples of the oil without the plaques. Now, you always do that. You always do that to make sure your food stimulating solvent isn't contaminated. There wasn't any plasticware that touched. I mean, shouldn't touch much plasticware, but if there's anything in your analytical system or workup or anything, you want to run your blanks so that you see that the peak didn't come from the sample. It was in your control, so it was in the blank. But this is critical for oil. When you cook oil at 500 degrees Fahrenheit, I mean, anybody that's ever run a fryolator can tell you it gets all this junky stuff in it, and I mean, it just burns and turns yellow and has all this stuff floating in it. And oil cooked without any plaque at all is a mess. Here's what the LC-MS of just the blank is. It has all these peaks in it. So what you're looking at when you look at the total line chromatogram mass spec, this is the PDA, this is the total line chromatogram, you've got a lot of peaks. So what you're looking for is peaks that aren't in this. Here's a 10-day migration of one of the samples. And yeah, you see some peaks come up, a couple of peaks that were not in the blank. And we identified these peaks with mass spectrometry as belonging to, related to the monomers. And we quantitated. Here is in the samples as a function of hours, one of the monomers, which is para-hydroxybenzoic acid, and how it in triplicate preps, how it went over time, and then there was one of the other peaks was a dimer of the para-hydroxybenzoic acid, which is the only thing that actually came out that was above the noise. For the other things, we just determine what the detection limits are. So here's a validation by standard addition. Using the method of standard addition, you can see it's perfectly linear, and so the method is valid with average recoveries of each monomer in the range of 90 to 110%, good precision, nice low limits of quantitation. Now, when you see something, you use the limit that's there, the value that you found. When you don't see it, you use the limit of detection to say, well, that's it's below that because I didn't see it, and that's the limit used for the food chemistry calculations. And we did that. We determined the concentration in food, M, using the concentration detected or the limit of detection when we didn't see it. We had 7.5 mils that we concentrated. And when you use oil, yeah, you can't just boil it off, but you can extract it into something like a liquid extraction with water, and then bring the water down. So you can do some tricks. And then you, in this case, for this particular application, we used 20 grams per square inch because it was a baking tray, and it actually was 20 grams per square inch of food contact surface. So since it's a particular object, you can use the actual weight of the product per square inch rather than the default of 10 grams per square inch. So per guidance, an article for repeat use assumes the migration limit, that is what you found, divided by the estimated number of uses, because after 1,000 uses, you throw out the tray. And so the monomers that were found were calculated to have 1.14 micrograms per day estimated daily exposure and 0.409 estimated daily exposure for the dimer, both below the threshold of regulation. The others were below the threshold of regulation because they were below the limit of detection, and the limit of detection was well below the threshold of regulation. And this FCN sailed through with only some clarifying questions and became effective. Another case study is printing on wrapper. We had someone that printed, used an ink to print on a wrapper, and the ink was, the dye in the ink was Sudan 1, which is known to be a problematic dye, but it's used in printing inks. Now, the ink was being printed on one side of the wrapper, and it was a wrapper for candy and gum. Actually, I believe the first application was gum, that also candy as an ancillary application. So they needed migration data to show that it was safe. So it's going to be packaged at room temperature. So room temperature storage, 10 days, 40 degrees C, 10% ethanol is an aqueous food stimulant. Now, you're not going to just take that wrapper and put it into a jar and fill it with food stimulating solvent, because that's really not fair to the process, because the printing is on one side. So you have to somehow generate a single-sided migration study. There are two ways of doing that. It was a small wrapper, so we'll show you what we picked. But you can use a migration cell. You can just, these are a little bit larger than the system we ended up using, which I will show you in a moment. But the migration cell, you basically put the paper wrapper across here, fill it with solvent, food stimulating solvent, and you can sample over time. The solvent is on one side of the wrapper, only the side not facing the food, which is the printing is not facing the food. So the stimulating solvent is on the other side, and you're sampling over time. What we did is use a Franz cell. So wrappers were small, and we had good limits of detection for the analytical method. So we printed the wrapper, put the wrapper in here, and the food simulating solvent is in this body, and this is how a Franz cell is put together. And well, this top part isn't important for a migration study. It's just used to hold the wrapper in place. And the printing side is on this side, and the food simulating solvent is on the other side. And you sample with a needle, and then the rest of this apparatus is just to circulate a medium to keep it warm, and to have a stir bar. And I'll show you what this really looks like. Here's ours. The water goes in one port and out the other port to keep it at 40 degrees C for a long period of time. And this is a multi-stir plate system, so it has 6 positions, and it keeps stirring so you can get some agitation. And this is how we did the system. That's how we set up the system, and did our migration study of our application, our ink. Okay, so the method was LCMS-MS. Here is Sudan 1 at 5.5 parts per billion. Signal to noise is 25:1, so limits of detection are around a part per billion. The migration showed nothing above the limit of detection. The limit of detection corresponds to 7 micrograms per kilogram in food. And 7 micrograms per kilogram would normally, in a normal food type product, would be problematic. But this was candy. This was gum, actually. Now, how much gum can a person eat? Well, marketing information is, can be used to knock down the EDIs. You don't have to use the default of 3 kilograms of food per day for every food. You can ask, well, what is the food? Is it realistic to eat 3 kilograms per day? Nobody's going to be eating 3 kilograms per day on average over their lifetime of gum. And 100 grams of gum a day, which would be a lot of gum and candy, quarter of a pound of gum or candy every day would be 0.7 micrograms per day, which is well below the 1.5 micrograms per day that would be of concern. So with this sort of argument about what this is being marketed for, this just went through with no problem. A cup. We had a coffee cup. So how do you deal with printing on the outside of a coffee cup? Well, again, you have a one-sided migration. In this case, you have an object. It's filled up to a certain level, and there's printing on the outside of this object, and you can calculate by some geometry what the surface area, inside surface area of the cup is. Now, for a coffee cup, we use 10% ethanol. We could have used water, but 10% ethanol accounts for the fact that there is often milk or some amount of free integrated fat into the coffee. And that accounts for, 10% ethanol accounts for that. 66 degrees is fairly hot coffee. And how long does coffee sit around anyway? A 10-day migration study doesn't really make sense for coffee. So 2 hours is more than reasonable for a coffee cup. And so we looked at this Sudan 1 in a standard and calculated the, again, we had our analytical method, and we did replicates. We have blanks where we didn't see it, and we were able to calculate the amount of dye that comes through the coffee cup into the coffee, and we're looking at 0.3 parts per billion in the diet, which is below the threshold of regulation. So this coffee cup is safe, and they don't have to change how they print their coffee cups. So in conclusion, when you're developing a migration study, you should design the migration study to reflect the actual conditions of use of the material as much as possible. Now, the guidances are guidances, but they don't anticipate every potential use of the product, and you are permitted to consider your reasonable potential use of the product and default to or work with the most severe conditions of actual reasonable use. Develop good, specific analytical methods that can be validatable, and target a dietary exposure of 0.5 parts per billion in the diet for your method. Consider real-world use of your products and the marketing of the product that you are going to be using it for in order to estimate consumer exposure. For more information about food contact testing, visit our website, and we will give you more information on the application and studies, or let our client development team know, and we'll be happy to put a quote together for you. Thank you for your attention.